now. Okay. Hello, everyone. Welcome back. So there's no class on the 21st because I scheduled this other class for like during the reading period for like an extra day to have the final presentation. So I figured since I'm scheduling one extra class, I should cancel one of the normal classes. So we're canceling this one, so you'll have like an extra long Thanksgiving break. Okay, so last time we were talking about Tableau, and we talked about the Robinson-Shenstedt correspondence, and I gave an example of this, where I said you start with a permutation, and you do this sort of bumping procedure where you build these two standard Young tableau of size n with the same shape, and this ends up being a bijection, although I didn't prove that. Then I stated the hook length formula, which gives you a formula for f lambda, which is the number of standard Young tableau of size lambda, or of shape lambda, I should say. So remember, we can think of a partition, like a Young diagram, as basically being a poset, where the boxes are the elements and the order relation kind of goes up when you go in the southeast direction. So whenever you go like to the right or down, that's going up in the poset. And then I was defining these operators. So I said you can define promotion, which, okay, so I defined it using first this like jeu de tacon sliding thing, where I said you delete the 1, and then you look for the smallest number that is to the right or below the 1, and you slide that in, and then you just keep doing this until you get to a corner, and then you fill it in with n plus 1 and decrease all the numbers by 1. But then I also said, well, you could also define promotion in this way, where we have these Bender-Knuth involutions that I've talked about before, and you just do bk1 and then bk2 and so on all the way to bk sub n minus 1. These end up being equivalent. And I should also say that you can do this for any poset. It doesn't have to be a poset coming from a Young diagram. So both definitions with jeu de tacon and with this make sense for any poset. So here P is an in-element poset. L of P is the set of linear extensions. Promotion will be a bijection from L of P to itself. So we know it's a bijection because each one of these BKs is an involution, so it's a bijection, so we're just composing a bunch of bijections. But I guess one thing I should say is that like each BK sub I is like a very simple thing. It's like a little involution. It's not very complicated. But when you compose them, then you get this more complicated thing. And then similarly, I defined this partial sub I to basically be like this partial promotion thing where you do bk1, bk2, all the way to bki. And then evacuation is this map where you do partial n minus 1 and then partial n minus 2 and so on all the way down to partial 1. Okay. So let me do an example of evacuation, and then I will say why I'm defining these things, because I haven't really told you like why would we care about these. Okay, so here's an example. So let's say I take this poset here, and I'll start with this linear extension 1, 2, 3, 4, 5. So I want to do, let's do evacuation. So I start by doing, okay, so here n is 5. So I start by doing partial sub 4, which is basically just the same as promotion. So this is partial 4. And, okay, so what do I do here? Okay, well, this is one of these like things that's kind of hard to do like in a lecture, because I don't want to draw out every single step, because that would be kind of a nightmare. So I'm just going to copy this and then do the Bender-Knuth involutions over here on this side. So if I want to do partial 4, I say, okay, I want to do bk1, which looks at the numbers 1 and 2. They are on incomparable elements, so I swap them. Then I do bk sub 2, so I look at the numbers 2 and 3. They are on incomparable elements of the poset, so I swap them. Then I do bk3, so I look at the numbers 3 and 4. The 3 is less than the 4, so I do nothing. And then I do bk sub 4, so I look at the numbers 4 and 5. The 4 is less than the 5, or is below the 5, so I do nothing. So this is partial 4. So now I want to do partial 3. Okay, so let me copy the post-it again. Something like this. So I'll have 1, 3, 2, 4, and 5. And okay, so now what I do is I say I'll do BK1, BK2, BK3. So for BK1, I look at the numbers 1 and 2. 1 is below the 2, so I do nothing. Now for BK2, I look at 2 and 3. 2 and 3 are on incomparable elements, so I swap them. And now I do BK3, which says look at the numbers 3 and 4. They're on incomparable elements, so I swap them. And that's it for partial 3. Okay, now I have to do partial sub 2. Okay, so let's copy this again. I have a 2, a 1, 4, 3, and a 5. So now I just do BK1 and BK2. So BK1 looks at 1 and 2. They're on incomparable elements, so I swap them. BK2 looks at 2 and 3. 2 is below the 3, so I do nothing. Now I do partial 1. Okay, so this is just going to be the same as doing BK1. So I have 1, 2, 3, 4, 5. And if I want to do partial 1, I just say, okay, I look at the numbers 1 and 2. They're on incomparable elements, so I swap them. Okay, so this, doing partial 4, partial 3, partial 2, partial 1, that is one example of evacuation. Okay, let's do it again. So, let's do partial 4. 2, 1. Maybe I'll go faster this time. Okay, so I want to do BK1. Then I do BK2. And then I do BK3. And I do BK4. So that's it for that. Now, partial 3. 1, 2, 3, 4, 5. So I do BK1. That swaps these. And then I do BK2, that swaps these. And I do BK3, that does nothing. Okay, now I do partial 2. So I have 3, 1, 2, 4, 5. So I do BK1 and then BK2. So BK1 does nothing, BK2 swaps these. And now finally I'm going to do partial 1, which actually goes here. Because all partial 1 does is it says do BK1, so I look at 1 and 2, I swap them, and if I do that, I get back here. So this is also evacuation. So an exercise that I put on the last P set is to show that evacuation is an involution. Which just means that if you do it twice, you get back where you started. And like this might not be obvious from this formulation, but well, you can prove it. So this is true. Any questions about that? Okay. So now let me go back and talk about more of the Robinson-Chenstedt correspondence. So remember I was saying that there are various symmetries that you can do to a permutation, one of which is you can take the inverse of the permutation. And on the level of the Robinson-Chenstedt correspondence, that corresponds to just swapping the two tableaux. So like the P tableau, so well, I can write this again.
Hey, Colin.
Yes?
So evacuation, if you do it twice, you get the original.
Mm-hmm.
But is there a way to see which ones just go to the original by doing it once?
Oh, yeah, so that's, I believe those are called self-evacuating tableau, which the name makes sense. I think that's what self-evacuating is. I don't remember exactly what they are, but I think they have been studied. Yeah, so those I think are interesting. Right. And they also have some connection with Robinson-Chenstedt, but I don't remember off the top of my head like what it is exactly. Okay. So here are some symmetries in the Robinson-Shenstedt correspondence. Well, okay, so I mentioned before that the insertion tableau of the inverse of a permutation W is just the Q tableau of W, so the recording tableau of W. And similarly that the recording tableau of W inverse is the insertion tableau of W. But there are various other things that you can do to a permutation, like you can reverse a permutation. So you can say, okay, well, what if I look at W times W naught? So remember, if you're thinking about the one-line notation of a permutation, this is just the reverse of W naught, or sorry, the reverse of W. This ends up being the transpose of the insertion tableau of P. Or of W, sorry. So you just reflected about the main diagonal. But if you look at the Q tableau of the reverse, this is the evacuation of Q of W transpose. So the reason why evacuation was originally introduced, I believe it was by Schutzenberger, he was trying to understand the symmetries of the Robinson-Shenstedt correspondence. And I guess one way you could think of this is there are these natural symmetries on permutations, like taking the inverse, or taking the reverse, or taking the complement, or the reverse complement. There's sort of like a dihedral symmetry group of permutations that you get by just looking at the plot of the permutation and doing like a rotation or a reflection or something like that. And then there are corresponding symmetries of tableau, or like pairs of tableau of the same shape that you can do. One of them would be you swap the two tableau, which is what you're doing here. One of them is to transpose a tableau, and the other one is this more complicated evacuation procedure. So it's like that's the role that the evacuation is actually playing. So I can write down another thing. We can conjugate by W naught. So if you think about this in terms of the plot of a permutation, this is just what you get by rotating the plot of W 180 degrees. This is the reverse complement. And this is just actually equal to the evacuation of the P tableau. And similarly, Q, so actually this seems even more natural than what I wrote for the reverse. It's just saying that evacuation really gives you the symmetry that you need to describe what happens when you conjugate by W naught. Yes?
So, in the context of a tableau, like BK1 is if you switch them, is it still a valid known tableau for BKI in general? Is that what it means?
Yes. Yeah. Right. So BKI says look at the numbers I and I plus 1 in your tableau, and if you can swap them and get another standard Young tableau, then you do that. Otherwise, you leave them alone. Okay. Okay, I mean, I could also write down other things like W naught times W, but I'm not going to. You could sort of deduce them from this. Okay, let's do an example, actually. Yeah, okay, well, I'll do an example without actually, like, going through the whole, well, actually, we can do it. Okay, so let's say W is, let's say we're in S5, and W is 4, 2, 1, 5, 3. And I want to apply Robinson-Shenstedt to this. So I want to get a pair of tableau. And I won't look at my notes, I'll just say, okay, let's do this. So remember, the first step is we insert the 4. So to insert the 4, I draw a box with a 4 on the P tableau side, and I draw a box in that position with a 1, because this is step 1. That's on the recording tableau side. Now I insert the 2, and the 2 says, okay, I'm going to try to come in here, but I can't put my 2 here because 2 is smaller than 4, so the 2 actually takes the place of the 4, and it bumps the 4 out, and now the 4 has to go to the next row, and it'll just sit down here. And so now, since I've added this box in that position, I add a box over here in that position with the number 2. And now, I want to insert the 1. So the 1 goes in here and says, well, I can't sit here because 1 is smaller than 2, so the 1 bumps the 2 out. Okay, but now we have a 2. Now the 2 tries to go down here. But also the 2 cannot sit here because 2 is smaller than 4. So now the 2 bumps the 4 out. And now the 4 comes down to the next step, but now the 4 can just sit here. And then over on this side, I added a box here. So I put a 3 there. Okay, now we insert the 5. This is easy. The 5 can just sit here. And so I add a box here. And now we insert the 3. So the 3 comes here and says, well, I can't sit next to the 5 because 3 is smaller than 5, so the 3 bumps the 5 out. Now the 5 comes down here, but the 5 can sit next to the 2. And so we've added a box there, so I add my box there. So this is my pair of tableaux of the same shape. So now, let's do the same thing for W conjugated by W naught. So, okay, I guess I didn't leave. Let me copy it down like slightly further this way so that I can have a little more room. 1, 4, 2, 5, 3. Okay. So now W naught is going to be 3, 1, 5, 4, 2. Right? Because if I complement this, like if I replace I by 6 minus I, this should be like 2, 4, 5, 1, 3. And then I read it backwards, so I get 2, 4, 5, 1, 3. So yeah, it's that. Okay. So I want to do Robinson-Shenstead to this. Okay, so what do? I insert the 3. And over here I draw a 1. Now I insert the 1, which kicks out the 3. So the 1 goes there. The 3 gets bumped down to here. So I write a 2. Now I insert the 5. The 5 just sits here. So I write down a 3. Now I insert the 4. The 4 bumps the 5 out. The 5 goes down here. Now I add a 4 here. And then I insert the 2. The 2 bumps the 4 out. The 4 comes down and bumps the 5 out. 4. And then the 5 comes down here. So I add my 5 over here. And now let's do evacuation to these tableaux. And the claim is that if I do evacuation to this, I should get this. And if I do evacuation to this, I should get that. So I do evacuation to this. Okay, so let me just copy it. One, 3, 2, 5, 4. Okay, so how do I do evacuation? Well, I do BK I do BK1, so I do partial 4 first. So partial 4 says do BK1, BK2, BK3, BK4. So BK1 does nothing. BK2 swaps these. BK3 does nothing. BK4 swaps these. So that was partial 4. Now I do partial 3. So I do BK1, BK2, BK3. So BK1 does nothing. BK2 swaps the 2 and the 3. BK3 does nothing. Okay, now I do BK2, or sorry, I do I do partial 2. So partial 2 does BK1, BK2. BK1 does nothing, BK2 swaps the 2 and the 3. And finally I do I do partial 1, which is BK1, which does nothing. And indeed, I did get the same tableau that I have there. So I did not make a mistake, I think. And then, let's do the same thing here. So I have 1, 4, 2, 5, 3. So I start with partial 4, so I do BK1, BK2, BK3, BK4. So BK1 does nothing, BK2 does nothing, BK3 swaps the 3 and the 4. BK4 swaps the 4 and the 5. Now I do partial 3, so I do BK1, BK2, BK3. BK1 does nothing. BK2 swaps the 2 and the 3. BK3 does nothing. Now I do partial 2, which means I do BK1, BK2. BK1 does nothing. BK2 swaps the 2 and the 3. And finally I do partial 1, which is the same as BK1, which does nothing. And so I did get the same tableau over there. Okay? So that's evacuation. I guess, okay, so promotion and evacuation are like these nice maps that people have studied in various contexts, and I'm not going to say everything that people have done with these things, although there's a nice survey that was written like in 2009 by Richard Stanley that's called Promotion and Evacuation, so that's kind of a nice thing to read. But here I figured I'd give one application of evacuation, which was the original application, which is to describe these symmetries of the Robinson-Chenstedt correspondence. And then I also want to give one application of promotion in the context of tableau. So maybe I should ask, are there any questions up to this point? Okay. So on the very first day of class, I think I mentioned that there's this really cool theorem due to Stanley, and it's an enumeration of the reduced words for the long element of the symmetric group. And so I'll write down this theorem again. And I think on the first day I said something like, I might prove this in class. I've decided I will not prove this in class, but I will at least, well, okay. I'll tell you the theorem, and then I'll say, I'm not going to talk about how Stanley proved this, but then there was another proof found by Edelman and Green using something called the Edelman-Green bijection. So I will tell you what the Edelman-Green bijection is, because I think it's very cool. I won't prove that it is a bijection, but I'll just say what the bijection is. Okay, so here's the theorem due to Stanley. I guess I didn't write down the year, but some year. Okay, so the number of reduced words for the long element in Sn is, well, actually, let me write it this way, is equal to I guess I'll say f superscript delta sub n minus 1, where delta sub n minus 1 is a particular partition shape called a staircase shape, and it's just the partition n minus 1, n minus 2, dot dot dot, 3, 2, 1. So this is the number of standard Young tableau of this staircase shape. And I'll just note, so if you want to actually write down explicitly what the number is, well, let me give an example. Let's say n is 4. So what does this partition look like? Well, it looks like a staircase. So it's 3, 2, 1. So you can see it's like, sort of a staircase, but maybe like flipped around. And if I want to compute what this number is, like the number of standard Young tableau, I can use the hook length formula. So let me fill in the boxes with the hook lengths, just so that we can see them. So the corners all have hook length 1. This has hook length 1, this has hook length 1, this has hook length 1. These boxes have hook length 3, right, because it's 3 and 3. And then this one has hook length 5. So in general, so by the hook length formula, F superscript delta sub n minus 1 is going to be the number of boxes, which is just n choose 2. And we do that factorial. So, right, it's the number of boxes factorial divided by the product of the hook lengths, which is going to be 1 to the power of n minus 1 times 3 to the power of n minus 2 times 5 to the power of n minus 3, and so on, until I think the last term is 2n minus 3 to the power of 1. Is this okay? Yes?
Sorry, what's F?
Sorry. F superscript lambda is my notation for the number of standard Young tableau of shape lambda. Yeah, I can write that. Okay, so Stanley, I think, proved this using symmetric functions. We're not going to talk about symmetric functions here. But I'll tell you the Edelman-Green bijection, which is an explicit bijection between reduced words for the long element of the symmetric group and standard Young tableau of this shape. No, and this should be, sorry, not lambda, it should be delta n minus 1. Okay, so here's the Edelman-Green bijection. Okay, so let me let capital N be n choose 2, so that when we're looking at the staircase, we're looking at a partition of size capital N. And then let's say T is some tableau of this this staircase shape. So T is a standard Young tableau of shape delta n minus 1. So what I want to do is number the corners of the staircase corners of delta sub n minus 1. So remember, the corners are just these boxes that have hook length 1. So number them, let's just say, as 1 through n minus 1 from bottom to top. Okay. So what I want to do, I'm going to take this tableau and I'm going to do promotion to it. But I'm actually going to iterate this. I'm going to do promotion multiple times. And so I'm going to define gamma sub k to be, well, okay, let gamma sub k be the number of the corner containing capital N in promotion to the k of t. So what I do here, so promotion to the k is just promotion composed with itself k times. I do promotion k times to t. I look for the corner that contains the biggest number, and then I write down the number of that corner, and that's gamma sub k. Okay, so let me do an example.
Wait, no, Colin, sorry. I'm slightly behind on taking notes.
Oh, that's okay.
Can I just take a picture?
Yeah. We're also recording the lectures.
Okay, thanks.
Okay. Do I have room to do this example on this small board? Maybe I don't. So maybe I'll do it here. Okay, so let's say n equals 4. And let's take t to be this tableau that looks like this. So I'll do 1, 2, 5, 3, 6, 4. And let's do promotion several times. Okay, so let me do promotion to t. One, 2, 5, 3, 6, 4. But now I want to do the Bender-Knuth involution. So bk1 does nothing. bk2 swaps the 2 and the 3. bk3 swaps the 3 and the 4. bk4 does nothing, and bk5 swaps the 5 and the 6. Okay. Now, okay, let me do this several times. Here's pro squared of t. So I'm going to do promotion to this tableau. Okay, so I do, maybe I won't keep doing the process, I'll just like write it down a couple times and then I'll just tell you what the answer is after a few steps. Okay, so I'll do 1, 4, 6, 2, 5, 3. So let's do promotion, so I'm gonna, bk1 does nothing, bk2 does nothing, bk3 swaps the 3 and the 4. bk4 swaps the 4 and the 5. And bk5 swaps the 5 and the 6. Okay, so now, okay, instead of just doing this several times, I'll just write down what you get for pro cubed. So this is going to be 1, 2, 4, 3, 6, 5. Pro to the 4th of t ends up being 1, 3, 6, 2, 5, 4. And then let me do one more. Pro to the 5th of t is that's the better way to draw a staircase. 1, 2, 5, 3, 4, 6. Okay, so what I want to do is write down the corners that have the biggest number, which in this case is 6, in each of these. So here, the biggest number is in, so this would be like corner 1, this is corner 2, and this is corner 3. In t, which is pro to the 0 of t, right? So pro to the 0 is like the identity map, so this is pro to the 0 of t. So in pro to the 0 of t, the biggest number is in the second corner, so gamma sub 0 is 2, because of this. And then for gamma sub 1, the biggest number is in the third corner, so this is 3. For gamma sub 2, the biggest number is in the first corner, so I get a 1. Here, gamma sub 3 will be 2. Gamma sub 4 is going to be 3. And then gamma sub 5 is 1. So the reason I did this is that I want to let, let's call it psi, or actually no, I was calling it psi, but let's call it EG for Edelman-Green. So EG of my tableau T will be the word that I get by writing down S sub the gammas. So I write down S sub, which way did I do it? S sub gamma 0. And then S sub gamma 1, dot, 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 S sub gamma capital N minus 1. So in this example, Edelman-Green of this tableau is S2, S3, S1, S2, S3, S1. And that is a reduced word for the long element of the symmetric group. And so the theorem is that this map EG is actually a bijection from the set of standard Young tableau of shape delta sub n minus 1 to the set of reduced words for the long element, which I think is pretty cool. Any questions about this? So I'm not like justifying any of this, like I'm not going to prove this stuff, but it's like magic for now. So, ta-da. Good. Okay. Thank you. Okay. Well, okay. So we can actually do something else with this. We can give sort of an application of the Edelman-Green bijection. So let me note something. Where's my? It's on my thing. Okay, so what would happen? I'll say note that. I can do Edelman-Green to promotion of T. All right, so instead of starting with T, I just start here, and I say do promotion this many times, starting here. So I would have like an extra tableau if I did Edelman-Green applied to promotion of T. And, well, what should this be? Well, the first capital N minus 1 letters in the word should be the same as what I wrote down here. The only difference is going to be what's at the very end. So this is going to be S sub gamma 1, S sub gamma 2, dot 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 S sub gamma capital N. So instead of going from gamma 0 to gamma n minus 1, I just go from gamma 1 to gamma n. Okay, so, wait, what am I writing here? Okay, so, what does this mean? Well, this is a reduced word for the long element, and this is also a reduced word for the long element. So, W naught is S gamma 0, S gamma 1, dot dot dot, S gamma n minus 1, but it's also equal to S gamma 1, S gamma 2, dot dot dot, S gamma n. And now from this equation, I can say then, well, okay, so S gamma 1, let's write down S gamma 1 through S gamma capital N minus 1. So I'm just taking basically the part of this word that is common to both of them. This is, well, I could write it as S gamma 0 times W naught because of this. But I could also write it as gamma 0 times, or sorry, W naught times S gamma n. Okay, so what this tells us, if I just look at this, I can multiply each side by W naught, let's say on the left. So, S gamma n is W naught S gamma 0 W naught. I just multiplied this by W naught on the left, so the W naught cancels here because it's an involution, and then I get W naught S gamma 0 W naught. Okay, but we know, if you remember how W naught acts by conjugation on the set of simple transpositions in the symmetric group, it basically just sort of, well, you can think of it as like flipping the Coxeter graph around. But here, okay, I'll just write it as thus gamma sub capital N is capital N, no, sorry, it's little n minus gamma 0. That's what conjugating by W naught does to a simple reflection. Right, so like, if you conjugate S1, you get S sub n minus 1. If you conjugate S2, you get S sub n minus 2, and so on. So, okay, this tells us something about these gammas. Right, it tells us that we started with gamma 0, which was just like, we picked some tableau, we wrote down this gamma 0, and then through this process, we said that, like, well, if you increase the index of the gamma by capital N, that corresponds to changing this number gamma 0 to n minus gamma 0. But I could do the same argument to say, well, if I ran through this, then I would find that, so similarly, gamma sub capital N plus 1 should be n minus gamma sub 1. And I could keep going. So, in general, if I take gamma sub capital N plus some number k, this should be gamma, or sorry, it should be n minus gamma sub k. And this is true for all non-negative integers k. So this sequence of gammas is, well, how should I say this? Yeah, okay, maybe I'll write it this way. If I started with t, so let's say I start with t, and I Okay, actually, I can write it formally. I didn't put this in my notes, but I think this is hard. So the point is that gamma sub, well, actually, I'll write it here. Sorry. Note. Gamma sub n plus k is the same, or no, n minus gamma sub k. What is n minus gamma sub k? This is what you would get. So is the corner, it's the number of the corner containing capital N in, well, pro to the k of T transpose. Right, so for example, if k is 0, then I'm just saying that, well, gamma sub 0 is the number of the corner containing the biggest number in T. But if I do n minus that, that's going to be the number of the corner containing the biggest number in the transpose of T. But this is just what I would get by taking gamma sub k if I started with T prime. So maybe I could write this as like n minus gamma sub k of T, where this notation means like the gamma sub k that you get by starting with T. This should be gamma sub k of T prime, the transpose. But because n minus gamma sub k is gamma sub capital N plus k, and because the Edelman-Green bijection is a bijection, this tells you that if you do promotion capital N times, you're just transposing your standard Young tableau. Okay, so since EG is a bijection, so bijection from standard Young tableau of staircase shape to reduced works for the long element of the symmetric group, it follows that if you do pro to the capital N of T, this is just T prime. So there's kind of this remarkable thing that happens where, you start with T, you do this weird process where you do all these Bender-Knut toggles like BK1, BK2, BK3, and so on. You just like do this so many times, and then magically, after you've done it exactly capital N times, you've arrived at the transpose of the tableau that you started with. And so then, as a consequence, well, if you do this 2 times capital N times, you get back to where you started, because then you've transposed and then transposed again. So pro to the 2n of T is just T. Cool. Does this make sense? Okay. So I think this is a good segue into an area that I'll talk about a little bit, called dynamical algebraic combinatorics. I guess the idea behind dynamical algebraic combinatorics is you have some interesting combinatorial objects like standard Young tableau or permutations or various other things, and you have some interesting combinatorially defined map, like in this case promotion, You say, what happens if I do this map? So this should be a map from your set of combinatorial objects to itself. You say, what happens if I just do this over and over? And in this case, there's like this sort of magical thing that happens where you start with your standard Young tableau of staircase shape, you do promotion over and over, and you find that after you've done it 2 times capital N times, you get back where you start. And so, in general, I guess, dynamical algebraic combinatorics sort of aims to understand this kind of thing. I guess I've kind of talked about something that I would also consider to be dynamical algebraic combinatorics when I talked about like pop stack sorting, because I said, well, you have like a lattice, which is like some set, right, with the lattice structure, and you have your map pop, which goes from the set to itself. And if you do this over and over, well, in that case, we know that you eventually get to the bottom element of the lattice, but you can ask things like, well, how many times do you have to do it to get to the bottom? Various things like that. Okay. So, yeah, let me just write sort of briefly. So let X be a set of, let's say, combinatorial objects. And we'll suppose that F is some map from X to itself. This is some interesting map. So some interesting function. And we want to study what happens when we iterate F. And by iterate, I just mean compose it with itself many times. Okay, and as I said, like one example could be pop on some lattice, which we've talked about. Another example, which I guess was in a P set, is this Krevera complementation map on non-crossing partitions. So this was this map K that was in one of the P sets. So Krevera complementation on non-crossing partitions. Right, so non-crossing partitions would be our set of combinatorial objects. We have our map, which is this K thing that goes from non-crossing partitions to non-crossing partitions, and we could say, like, what happens if we do this over and over? And I guess another example is what we've been talking about now, which is promotion on the set of linear extensions of a poset. I guess you could also do evacuation. I erased it, but maybe from the dynamical point of view, evacuation isn't super interesting because it's sort of interesting, I guess, depending on the question you ask. So maybe like the question that Yunso asked is interesting in the sense of we know it's an involution, so, well, like everything just, if you do it twice, you get back to where you started, but you could ask like, okay, what are the linear extensions that are fixed by that? So, okay, that's an interesting thing, I guess.
Also, maybe stack sorting?
Yeah, you could also do stack sorting, yeah. I guess I haven't talked about that, but yeah, you could take your objects to be permutations.
Did you talk about that?
Oh, I mean, I maybe alluded to it. I don't think I said anything specific here. But yeah, you could do stack sorting or other pattern avoiding stacks from a dynamical point of view, which Ilaria studied over the summer. But yeah. So, let me tell you some dynamic, I guess I'll focus mainly on promotion here. Let me tell you some dynamical things. So, well, I guess first of all, this is due to Edelman and Green, and it's basically what I just told you about. Edelman, Green, 1987. So I guess I'll just say the order of promotion viewed as a map from the set of standard Young tableau of staircase shape delta sub n minus 1 to itself has order 2 times capital N, which is n choose 2. Or in other words, it's, if I think of the staircase shape as a poset, this is just 2 times the number of elements of the poset. So I guess I could write this as like 2 times the size of delta sub n minus 1, and by that I mean like the number of boxes in the staircase. But actually there was an earlier result. I'm going a little bit anachronistically here. This is Schützenberger. Schützenberger. This was 1977. So I'll just say if P is a rectangle poset, and by rectangle I mean it's the poset that you get by a rectangle Young diagram, if you think of it as a poset. Then, oh, maybe I should say what I mean by order. Order is just like, okay, see, so you have this invertible map from the set to itself. So it's going to partition your set into these orbits. And the order is just the least common multiple of the orbit sizes. In other words, it's the smallest number such that if you do your map that many times, you always get back to where you started. So here, if P is a rectangle poset, then the order of promotion from, well, I could call it standard Young tableau, or I could just say linear extensions of the poset, same thing, is, in this case, it's equal to the size of the poset, so without the 2. Okay, so, well, let me just mention these theorems because I guess it's good to mention them. This is due to Heyman from 1992. Although I won't really explain exactly what the poset is. So, okay, if P is a, okay, so he calls it a shifted double staircase. This is some poset, so shifted double staircase. Or, okay, there's another type of poset that he considers, a shifted trapezoid. So these are some particular families of posets that have some shape that you can write down. Shifted trapezoid. Then promotion has order equal to the size of the poset. then I'll mention one other result. So this is quite recent. This is due to Sam Hopkins and Martin Ruby. I think it was published in 2022. So if P is a chain of V's, so I'll draw an example of what this is. A chain of V's. So it's some poset that looks like a chain of V's. Then in this case, the order of promotion is 2 times the size of the poset. And a chain of V's looks like this. You have this V, so this is a V, it's just literally 3 elements that look like that. And then you draw another V like below it. You connect them sort of like this. Then you can keep drawing these V's as you go down. I'll go one more. So I'm going pretty low. Hopefully the recording can get this, but that's generally what a chain of V's looks like. Okay. And I don't know how genuine this is to say, but I guess like in some sense, what I've written down on this board is like all of the examples that we know of like families of posets where the orbit structure of promotion has nice behavior. Or like we can very nicely write down what the order is. So usually if you just like give me your favorite poset, say, okay, here's some poset, and it's like not on this list, and you ask like, what is the order of promotion on this poset? It's probably gonna be some awful thing. There's probably, like, it's just gonna be a mess. And so it's kind of like, these are the miracles that happen to happen. Like, okay, so I guess like these were, for a while, the only ones that we knew, and then Sam Hopkins was like, well, let me try to search for something else, and he came up with this example. But yeah, like these are sort of the isolated miracles that we know about, and then everything else is just awful. Yeah. That's kind of a theme, I guess, in dynamic algebraic combinatorics. It seems like very often you have like these nice particular miracles, and then everything else is just awful. And then like the goal is to try to find the miracles, like, you know, hiding. Okay. Any questions on this? So, okay, I guess what I'm talking about here is the order of promotion. So you have like, you have your promotion map, and it's breaking up the set of linear extensions into these orbits. And this is just talking about the order, which is the least common multiple of the orbit sizes. But you could say, well, like, what are the orbit sizes? Not just like, what is their least common multiple? Can you like write down like the multi-set of orbit sizes so that you're really characterizing the dynamical behavior of this map? And so there's this nice, I guess, definition that was given in, I didn't write down the year, but I think it was 2004. So this was Nick Reiner and Dennis Stanton and Dennis White. I'm pretty sure it was 2004. So this is sort of a general definition that you can apply whenever you have some setup like this and the map F is invertible. So let X be a finite set. So So in your head, you can think of this as like the set of linear extensions of a poset, for example. So it's a finite set. And suppose we have some map, f, from x to x. And we'll suppose this is a bijection. So since it's a bijection from x to itself, it's going to split up the set x into these orbits. And we'll say that it has order omega. And I want to let capital F of Q be some polynomial, I guess let's say with, I don't know, complex coefficients. Yeah. So it's some polynomial in the variable Q. Then we say that the triple x f capital F of Q exhibits the cyclic sieving phenomenon. The cyclic sieving phenomenon if, so I'll write it down and then try to explain what it's saying. If for every integer k, the number of elements of capital X fixed by the kth iterative f is the evaluation of this polynomial capital F at the root of unity e to the 2 pi I k over omega. So what is this saying? I guess I'll give an example also, and then maybe I'll be out of time. So if I have my map, and I can say for every integer, how many elements are fixed by like f to that integer, that will determine the orbit structure, right? Because in other words, saying that an element of x is in an orbit of size m is really the same as saying that that element is fixed by f to the m, or really any, like f to n to the power of any multiple of m. So if you can understand what all of these numbers are, like the number of elements fixed by f to the k for all k, that is really the same as describing the entire orbit structure of this map. And what this is saying is that sometimes you can find some polynomial so that these numbers, which are describing the whole orbit structure, are exactly what you get by just plugging in these roots of unity into this polynomial. I should say that in general you can always find such a polynomial f by just sort of interpolating these numbers. You just do like a polynomial interpolation. The interesting thing is when the polynomial is nice. So it's not just like, oh, write down this like 30-term mess, expansion of q's. It's like if there's some nice formula for it, that's sort of what people are interested in. And then the goal is like, okay, can you explain why you have this nice polynomial showing up? So let me see if I have time. I might have time to quickly do an example. Okay, so let's consider so it's promotion from the set of standard Young tableau of shape 3, 3 to itself. Okay, so what is this going to look like? Here are my tableau of shape 3, 3. So I have 1, 2, 3, 4, 5, 6. And 1, 2, 5 3, 4, 6. Here's going to be 1, 3, 4, 2, 5, 6. This one is 1, 2, 4, 3, 5, 6. And this should be 1, 3, 5, 2, 4, 6. Okay, now I could compute promotion for all of these. I did this in advance. I'm not going to do it right here. I'll just say that if you compute promotion, you find that promotion sends this tableau to this one. It sends this one here, sends this one here, and it swaps these two. So these arrows are giving what promotion is doing. So let capital F of Q be, okay, so it's going to be 1 minus Q plus Q squared times 1 plus Q squared plus Q cubed plus Q to the 4th. Okay, so if I do capital F of E, so first of all I should say the order of this map is 6 because we have 2 orbits. They have sizes 3 and 2. The least common multiple of 3 and 2 is 6. So the omega from the cyclic sieving phenomenon definition is going to be 6. And if I take e to the 2 pi I, let's say, times 1 over 6, so here I'm setting k equals 1. You can work this out, I guess, and you end up getting 0. And that corresponds to the fact, so the claim is that this triple, the set of standard Young tableau of shape 3, 3, with promotion, and then with this polynomial, this will exhibit the cyclic sieving phenomenon. So this is 0, which is the same as saying that there are no elements of my set that are fixed by promotion to the power of 1. Right? Like there are no fixed points here. That's what this is saying. And you could work out that f of e to the 2 pi I times 2 over 6 ends up being 2. And this corresponds to the fact that if I do promotion twice, these 2 elements will be fixed. So there are 2 elements that are fixed. These are not fixed. And you can keep going. F of e to the 2 pi I 3 over 6 ends up being 3. That's because these 3 elements are fixed by promotion cubed, but these are not. And then I guess I'll just write down a few more. F of e to the 2 pi I times 4 over 6 is 2, because those 2 elements are fixed and those are not. F of e to the 2 pi I 5 over 6 is 0, and f of e to the 2 pi I, okay, well this one, what is, if I take e to the 2 pi I 6 over 6, well that's just e to the 2 pi I, which is 1. So I'm taking f of 1, which in this case is, I guess, 5. Yeah. And that's because all of these elements are fixed by promotion to the 6th. And so the point is that all of the dynamics of this map is encoded by this polynomial here. And it turns out that, okay, I wrote down this polynomial like this, but there is a more general form that you can write down that will tell you a cyclic sieving phenomenon for promotion on any rectangle shape, like the standard Young tableau of any rectangle shape. That's what I'll tell you about next time. It's a very cool result due to Brendan and Rhodes. I guess for now, this is all.